Licentiate seminar from Raj. Raj is a PhD student in mechanical engineering. He's going to present today his Licentiate, which is the result of a journey started slightly more than 2 years ago. I am Alessandro Bertoni. I've been the main supervisor of Raj in this last 2 years. And together with Johan Wall, we have been guiding Raj through this journey right now. And in this event, we have one opponent and one examiner. The opponent is Professor Fredrik from Jönköping University. And the examiner, which is the one who actually say at the end if this is passed or not, is Professor Tobias Larsson from BTH, who is sitting there in the back of the room. So how is this day going to be organized? We're going to start with Raj presenting for 25-30 minutes. Then we will have a 5-minute break to reshape the room. We'll have 2 tables, and the opponent will take place in front of the audience, and we'll start a discussion with Raj on whatever he thinks is relevant for the thesis. This discussion, it takes as long as the opponent feels is required to discuss that. After it, we will have the chance for the public, for the audience to ask questions. We start first with the audience in the room, and then we open to the audience online. We have quite many people following on distance. So for the online audience, we will be able to ask questions using the chat of the Zoom room, or if you want to talk and you have the possibility to talk with the microphone, you can raise your hand or ask this for you to be unmuted and then ask questions. After all these steps, it will be the time for the examiner to take a decision. He can take a decision right away. He can decide to talk with the opponent, to supervisor. He will be deciding what he prefers is the best out of what he has listened and what he has read in the thesis. Having said that, I just want to remind that we have someone actually taking care of the online session. If you have any problem or troubles, you can contact via chat. And we want to make sure that everyone can actually listen and everyone can ask questions at the end. That was pretty much everything I had to say. So now I leave the stage to Raj, and we start with the presentation.
Hello. Yes, thank you everyone for joining in offline as well as online. And thank you for taking the time for listening to my presentation. I'm Raj, as my supervisor Alessandro introduced me, and my thesis is titled Towards Changeability Quantification for Product Service System Design. I dive directly into the motivation by giving a very simple example. Everyone uses a smartphone. This phone can do so many features or so many things for you, and it's such a versatile product. You want to make a call, it can do that. You want it to behave like a camera, it can do that. You want it to be your navigator, it can do that. You want it to be the calculator, it can do that. So you see, in all these cases, there was a change in the requirement, and that requirement was fulfilled by the same device, the phone. But there could be a change in the context as well. And I take the example of the same phone. See, you are not in an environment that you're used to. You're in a place in nowhere. You've lost your internet connection or your network. You still have the requirement of call. You make it by the satellite communication. And today's phone, I think, can do that. Your same hardware, your flash, can be used as a torch if you are in the dark somewhere, which away from the home. Your same GPS now can track your steps if you are on a day hike. So the moment your context changes, your phone can manage these kind of new requirements, and I can go on and on. So what exactly I'm coming to here is that whenever we develop some product or some device or some system, it has inherently some value associated to it. And if nothing changes, it will keep delivering that value. But in case of changes in the form of context or requirement, we could have that system depreciating its value. So for example, now there was a new requirement of taking a snap. If there was no function of camera available, you would the value of it would drastically depreciate. But now it still does the job. I mean, maybe not as good as a DSLR, but so how much the value is appreciated depends on the application. But still, it fulfills the function. There might be instances when you cannot really help value depreciation. An example of this is constant charging cycles will depreciate the battery. I mean, if you have a modular battery, you could swap it out, but in today's phones, I think you cannot really help that value depreciation. There might be cases when the value depreciates because of the functionality. Now imagine a case in extreme weather. You have your gloves on your hands and you feel like, oh, I wish I had a button on this phone so that I could make at least a call. But the thing is, you don't really change the product just based on one instance. What the goal is to achieve or do this cycle repetitively and come to a conclusive of what exactly is the value with respect to time, and the goal is then becomes to achieve value robustness for this product. Now this was a relatively simpler product where we just saw the system could change in the form of there could be changes in the form of requirements, changes in the system itself, and changes in the context. But now imagine an operational scenario as complex as this. You have many haulers working together, in trucks as well, in coordination with wheel loaders, excavators. There are several infrastructures that these machines interact with, such as the screener, the crusher, the power grid. There are environmental factors, such as the gradients of the road, the ambient temperature, the frictional properties of the path, and so on. So what exactly should change and why? And usually the system changes depending on the changes in the context, or what we refer to as external changes. And when I come back to this image, usually a company develops a function, develops a product or a product service system to achieve a goal or a function. And in case of product service systems, you usually have or can have changes in your product, in your services, or in your infrastructure. So to summarize the motivation, complex systems such as the one I have shown, it's again a hauler from a mining scenario, undergo a lot of uncertainty in their operational phase. This can be changes in the requirement, context, and so on. These changes inculcate risks that the developed system may not be able to deliver the intended value. But if we are able to somehow change this system so that it can resist those value depreciating events, then we can say that we have developed a so-called value robust system. So what are the complexities? Well, any system that we develop, such as a product service system, inherently has structural and behavioral complexity. Now, what I mean by this is that the structural is the way the components are arranged, and behavioral is the way it achieves the function. Assuming that we want to maximize the utility or the performance or the benefits of this system, then under a given context, we usually, based on the number of design objectives we have, it's typical to trace out a Pareto. And it is worth noting here that the context still is fixed. In a given context, try to maximize or at least see what are my Pareto fronts. But if we inculcate this time perspective, this context keeps changing. And then the goal becomes to evaluate a new Pareto front that will enable us to see what is a suited design, not just in one context, but in all contexts. Now, I have this example as two objectives. There could be n number of objectives, and this space could become multidimensional. But value-driven design theory brings us to have one singular value for a product to basically have distinguished each design in which is the better one compared to the other one. So for example, in this case, when I had two objectives, utility and cost, I could say that the value is a ratio of utility to cost, and then I have a single value. So in a given context, again, reducing the dimension of that Pareto to 1, we see that we have several design points that have different values. Assume that we choose the one that is the best one, the red one. Why not? Because it has the best value, better than the green one. But does it really have the same value when the context changes? In the next one, maybe yes, because it's still better than the green one, but there is a possibility of another design that was perhaps suited better. And in the third case, the value depreciates drastically compared to the green one. But then should we have chosen the green one? Well, that's not the groove of changeability. What if we could have this design such that it could take the form of the red one in the first context, the red one again in the second, and the green one in the third one? So a combination of red and green. And that's where we would like to quantify changeability. So changeability quantification is necessary because we cannot have a system that can do all the jobs. There has to be some sort of a balance. And that is because the more changeable systems you have, of course, the cost of change decreases, but at the same time, the cost of investment increases. And we are not looking for like the most changeable solution or not changeable solution. We're looking for a sweet spot that gives out the best balance of how much changeable our system should be. With this background on changeability, I come to the research question that I've defined, and it reads, how can changeability be quantified in early design to support the development of value-robust product service systems? To reach this goal, I have 3 objectives defined. The first one reads, emphasize the challenges concerning changeability quantification for value-robust PSS design. The next one is, support early design trade-offs in PSS by integrating design variables, state variables, control strategies, and contextual variables. And finally, outline the state of the art in data-driven value creation for product service system design. In regards to the research method, the results that I will be presenting today are an outcome of design research methodology in the form of iterative cycles of descriptive and prescriptive studies. The approach has been participatory action research, and 2 company partners, the collaboration had been with 2 company partners, Volvo Group and Dynapack. So let's have a look at a formal definition of changeability. Let's say that we want a system to take a new state in a given time from this circle to the rhombus. It could have several options that it could take to reach that new state. And these options are basically the mechanisms that we have inculcated in the system to take a new state. And then it's basically dependent on the system which path to choose. But then each path will also have the cost associated. Take an example of the mining scenario that I showed you in a hauler. Your requirement has changed, and now you need to transport more material in the same amount of time. What are the options? You have a requirement of, you can increase the speed, or you could increase the payload capacity. So you see that for the same effect, you have multiple possibilities, and then you have multiple costs associated to it. So in the form of agent mechanism effect framework, how we define changeability as there is always a change instigator. It could be an internal agent or an external agent that drives the change. The mechanisms are all these options that the vehicle can choose. And then effect is the change in the state of the system. Coming back to the research objectives, which were, what are the issues in this quantification? And here I highlight a few points. The first one is, for changeability quantification, a unified view of system configuration, control, and control variables is needed, along with all the influencing context. The next one is, Changeability in PSS especially is difficult because it is applicable to the entire domain of product of components, such as the products, the services, and infrastructure. So now you have to balance out which one should change. The third one is higher degree of unbounded states in PSS. It requires an educated guess to confine the design space of what are my reachable states. And finally, changes in the form of software and services are relatively easier and quicker, but are difficult to predict and to model and simulate. So to address these challenges, literature was overviewed thoroughly, and the methods that exist in literature were tried to fit to the purpose. And turns out these are the three core methods that have been utilized to achieve a step towards changeability quantification. The first one is design optimization, second one is dynamic programming, and the third one is discrete event simulation. Coming to dynamic design optimization, this is an overall picture of how it works. You start with defining a problem in the form of objectives. Then you generate several solutions. Let's say you have n number of solutions. Then the optimizer or an algorithm would model this solution based on the design constraints. And then there is a simulation of the system to generate the responses of the system based on the configuration. And these responses are basically the states of the system. And then you repeat this cycle for the n number of solutions. And once the stopping criteria is reached, you reach the so-called optimized solution. In this framework, it was enhanced by adding dynamic programming in the simulation part, just to be able to simulate context in a much detailed level. So here you can see that the global optimizer is the same, and the simulation was performed in dynamic programming. What benefit it gives us is that depending on how we have discretized the simulation, it could be a time-based discretization or a spatial discretization. We could fine-tune our control strategy based on the value function that we have defined. So again, that same cycle, a bit more in detail, we have the system, we have its design variables and its state variables. Now here, specifically the design variables would contain configuration and control variables are fed to the optimizer. It configures a viable system based on the design constraints. Based on the configured system, then we have its control variable grid and its state variable grid. And this is a little bit up to the user, how much is the discretization and how much is the time span that you want to simulate for and so on. Such a grid is fed to dynamic programming algorithm, which also takes the inputs from several contextual variables to simulate an optimal control strategy based on the control constraints. And eventually, we get a so-called optimal control policy. Is something that how this system should perform in the given context. And then the global optimizer takes these outputs and then tries to map the Pareto front of as many variable objectives as we have. So to test out this framework, again, the same case was used, is the mining scenario. And a new electric hauler that will eventually be in these mining scenarios was tested. And in order to do so, we developed a vehicle dynamics model of this hauler along with its transmission, motor, battery, and so on. And such a model was then simulated to see how well it performs. And this is a completely or fully electric hauler. On the application of the framework, here are an exemplary results. As you can see that we have a Pareto front mapped for total time required and total cost of operation. You can see intuitively that as the payload of the hauler increases, so does the time required to achieve the same job. Moving a specific amount of ore from one point to other decreases. But so because of the fixed cost, and the operational cost increases. More interesting here is that each of these gray boxes show one specific configuration of the hauler, and the dots within those boxes are different control strategies. So for example, between design point A and design point B, there is a change in configuration. But between design point B to C, there is a change in control. And what in this case, it is one of them is speed. And to give a little bit of an intuition here, let's say if we were to increase the speed of design point A, it might not be the most optimal way to do so, because there is a design option available, point B, that could do it better at reduced speed. So this is how you could simultaneously see different configuration and control strategies. And as an example of how these control strategies work, I have a graph that shows the velocity profile of a hauler. And you see that the black line indicates the gradient. The green and red lines indicate the velocity profile. The red is the one when it is loaded, and green is when it is unloaded. And accordingly, the state of charge of the battery, which is the blue line, can also be calculated. And you see that we have, based on a different control strategy, you can have a different velocity profile and state of charge as marked by the dashed lines here. But this is simulating one hauler. In today's world, we need a system of system perspective, because we usually have many haulers working in a mining scenario. And in order to do so, we expanded this framework by adding discrete event simulation to it. So as you can see, the global optimizer position is still the same. It does not include discrete event simulation because this exploration was, enhancement was mainly based on the principles of design space exploration. So for several different haulers, such a simulation is performed, and then the data is stored in the form of different configuration and control strategies, and then is fed to a discrete event simulation. In a discrete event simulation, state change within a system are only allowed at discrete points in time. So you see that at each of these junctions, EI or EJ or EK, that's where only the state change in the system is allowed. In between, there is no control. So what this framework adds is, especially because of dynamic programming and the discretization of the transition between these two events, we can add some dynamism and see what different control strategies could be used. So with this expansion, again, I have a picture of a discrete event simulation tool where we have an operational scenario, a mining site, and we have several different infrastructural points or event points modeled, such as the crusher, screener, charging stations, and so on, enabling us to then define different paths along these along this mining site, connecting all these infrastructure to see what are the best suited number of haulers and how we could really achieve the required production. So we have a point of stockpiling, we have some a point of charging, and then we have the paths that haulers take to eventually simulate in a discrete event simulation. So evaluating this support from framing it again on the 5 complexity aspects, from starting from structural, this works reasonably fine up till contextual complexities. But the moment we try to scale it to temporal complexities, you have 2 challenges. One of them is computational complexity, which is the cost of computing all the contextual changes, and the lack of contextual knowledge, which means that we really don't know what all changes could happen and really which one to prefer and which one to not. But at the same time, with the advancement in digitalization and IoT, we have a lot of operational data that we could collect now. And hence, this path was chosen so that we could see how we can address these challenges by using operational data. Again, restricting this study two operational scenarios and to see what kind of data is collected and how it is utilized. We filtered out in a systematic literature review all the papers that go beyond an operational scenario to enable us to see what kind of data is collected in the product service system along with its associated context, which is basically the interaction of these two to generate operational data. Within the PSS, we found product-oriented data comprising of 3 classes: specification data, usage setting, how the user wants to usually uses it, and the result of it, what is the outcome of the way it used. There is service-oriented data. So what kind of service configurations were applicable at that moment, and maintenance log, how much is the uptime, or how many components fail, and so on. Infrastructural data, what is the capacity of infrastructure, how does it function in collaboration with these machines, and so on. And there is a lot of contextual data, and one of the pillars is, of course, the environment oriented data, which basically boils down to 2 broad classes: weather and locality. And here I mean by what kind of weather conditions were applicable during that, and locality means the geographic location of it. That would define how were the gradients and how were the contexts around it. And finally, human-oriented data, again, can be classified into 2 classes: attributes and state. What I mean by attributes is basically the human attributes like education level, the age, preferred hand, and so on, and the state. What kind of a mood was the user in when the machine was operated? What was the state? Was it stressed or not, and so on. All this data could really help us to achieve some form of improvement in the product service system, eventually understanding value better. Hence, to conclude, coming back to the research question and to the objectives, the first objective, there were several challenges that were highlighted concerning changeability quantification, ranging from generic to the ones specific to PSS. Research objective 2, a framework is proposed combining design optimization, dynamic programming, and discrete event simulation to facilitate a better understanding of value of a PSS in different operational contexts. Here we have 2 challenges. One is computational complexity, and the other is lack of contextual knowledge. And regarding a research objective 3, a systematic literature review featuring state-of-the-art in collection and utilization of operational data is presented. As a part of limitations, these are preliminary results of a wider research effort, and it can be positioned at addressing the 5 complexity aspects in design decision-making. The problem identification and investigation of the rationale behind the proposed framework is limited to 2 industrial partners sharing similar challenges. The generalizability of the findings in different industrial contexts featuring similar challenges in regards to SE and PSS, systems engineering and PSS, shall be further investigated to strengthen and refine the presented results. For changeability quantification, the design alternatives need to be characterized in terms of cost of investment and cost of change. Such a characterization shall be investigated as a next step. Complete determinism may risk in decision-making, which is quite contradictory to achieving value robustness. As you can see, this framework was dependent on a deterministic dynamic programming. However, adding stochasticity to the proposed framework is possible. Future scope, as obviously, the first step would be to integrate the operational data to support addressing, I think, both lack of contextual knowledge and computational complexity. Several integration opportunities exist, right from just having simple probabilistic distributions to advanced machine learning algorithms. Approximating the value or policy space by reinforcement learning can be a crucial advancement to this framework to at least reduce the computational complexity. What I mean by this is that dynamic programming is really a global optimizer. It tries to find out by evaluating all possibilities. We could approximate that by reinforcement learning. It's an enhancement of dynamic programming. And finally, coupling simulation data with game engines to visualize the results or to partially simulate in these game engines is deemed suitable for further investigation to address perceptual complexity. With this, I end my presentation by thanking you all and thanking my team, my colleagues, my supervisors, and my family for being supportive through this journey. Thank you, everyone.
Thank you, Raj. Now we take a 5 minutes technical break for rearranging.